Okay. So, that it is continuation of that previous topic, that is characteristic of your transmission line performance and characteristics. So, we will take another example, right. To take after this one more example, and after that we will go to some another regarding your voltage waves, right. So, it is this one earlier we have seen that your short circuit line medium also with pi your pi model of the transmission line, and now this one we will see that your what you call the exact one, that is the long transmission line, right. And after this we will take one short line, medium line and long line, and with the same parameters, and we will compare. That will be the next example. So, it is a long transmission line, it is delivering a load of 60 MVA at 124 kV 50 hertz and 0.8 power factor lagging, right. Resistance and reactance are given, right, and admittance due to charging capacitance is also given 0.442 into 10⁻³ mho. You have to find out ABCD constant, sending end voltage, current and power factor, regulation and efficiency of the line. So, resistance is given 25.3 ohm, X is 66.5 ohm, and impedance, and hence impedance is 25.3 plus j 66.5 ohm, and gamma Y is equal to that charging admittance j 0.442 into 10⁻³ mho. This is the charging admittance, and gamma L, because we are going for a your what you call long line thing. So, gamma L actually root over z y, and this is actually small z, right. So, small z y into L is equal to you can write root over, it is actually inside if you bring L square. So, z L into y L, that is actually gamma L is equal to root over capital Z capital Y, right. Because and z and y both are known to you, this is z and this is y, both are known to you. Therefore, root over z y is equal to, this is z and this is y, you will get 0.0327 plus j 0.174. So, A is equal to D, that is ABCD parameter for long line, it is cos hyperbolic gamma L. So, cos hyperbolic root over z y is equal to cos hyperbolic, this value you substitute here root over z y, you will get A is equal to D is equal to 0.986 angle 0.32 degree, right, and B is equal to ZC sin hyperbolic gamma L, right, and G is equal to, you can write root over ZC is equal to root over Z by Y, capital Z upon capital Y. Earlier also we have all these things have been given, all these term and definitions. So, sin hyperbolic root over Z Y. If you substitute this thing root over Z by Y, if you compute, it will be 393 minus j 72.3, and hence this B if you substitute here, you will get 70.3 angle 69.2 degree, and C is equal to 1 upon ZC sin hyperbolic gamma L. So, it is 1 upon ZC. So, hence it is root over Y by Z, capital Y by capital Z, sin hyperbolic root over ZY. So, if you substitute all these values, you will get C is equal to j 0.44 10 to the power minus 4, right. So, that is your all the ABCD parameter computation for long line. These are over. Now, next is at that your part B, that you have to find out the sending end voltage, current and power factor, that is the part B. So, load at 60 MVA is 124 kV. If nothing is mentioned, means you have to assume this is line to line. So, this voltage is line to line, right. So, load current same as before, right, root 3 your VI is equal to MVA. So, it is 60 into 1000, right. So, it is basically magnitude of the current is 279.36 ampere, right. So, and this one power factor is 0.8 lagging, right. Therefore, IR is equal to 279.36 angle minus 36.87 degree ampere, because power factor is 0.8 is lagging, right. So, here your what you call that VR is equal to you take, I told you that you have to take everything in line to neutral, that phase voltage. So, 124 upon root 3 angle 0 degree kV. So, it is 71.6 angle 0 degree kilovolt, that is phase voltage. Now, you know that sending end voltage is equal to AVR plus BIR, right. So, this current is actually 220, you are called 279.36 angle minus 36.87 degree. That means, this Vs is equal to 0.986 angle 0.32 degree into 70, what that is AVR 71.6 angle 0, and this is your B value 70.3 angle 69.2, and this current is 279.36 ampere. So, divided by 1000 such that it will become, this whole quantity will become in terms of voltage drop will be kilovolt, right, angle minus 36.87 degree, because this is kilovolt, right. So, you will get Vs is equal to 87.84 angle 7.1 degree kilovolt. So, sending end voltage L dash L means line to line, the root 3 into 87.84 angle 7.12 degree kilovolt, that is 152.14 angle 7.12 degree kilovolt, right. Now, sending end current I s is equal to CBR plus DIR, C and D both have been computed, right. So, and VR is known, IR also known, right. So, all these value you substitute here, right, here you substitute and compute, you will get that I s is equal to 257.78 angle minus 30.86 degree ampere, right. Therefore, this then to find that you take a reference line, this is your reference line, your Vs is 152.14 angle 7.12 degree. So, leading from this reference line. So, this is your Vs 7.12 degree and current is minus 30.86 degree. So, this side 36.87 degree. So, angle, the power factor angle will be angle between the sending end voltage and this sending end current. So, it will be 7.12 plus 30.86 degree is equal to 37.98 degree, right. So, this is that your power factor angle. So, once you get this power factor angle, so you take this as a sending end power factor, that is cosine of 37.98 degree, that is equal to 0.788, right. This is a sending end power factor. Now, third part is that you have to find out the regulation, right. So, Ps is equal to sending end power is equal to root 3 your Vi, this is your one line to line, this is your 152.14 kV into your 257.78 cosine this one divided by 1000, because this is in ampere and that is why we have divided by 1000. So, and this is in kilovolt, this will be kilo ampere. So, ultimately it will become 53.52 megawatt, right, and receiving end power 60 into 0.8. So, 48 megawatt, right. This is your 3 phase power, right, and this is 3 phase sending end power. So, 53.52 receiving end is 48. So, efficiency is your what you call 48 upon, that is PR upon PS, this we know. So, 48 upon 53.52 is 89.68%, right. This is the efficiency of the line. It was then this D actually it was given in D efficiency of the line, but here itself we have computed, right. And voltage regulation is mod Vs upon A minus mod Vr divided by mod Vr. Vs is known, magnitude of Vs is known, magnitude of A is known, magnitude of Vr is all known. You substitute here. So, if your voltage regulation is 24.43%, right. So, this is actually, if you have this example is considering a long transmission line, right. Next one is for this long transmission line, this is an example where same data have been taken and used for short line, medium line and long line. So, a 60 hertz 250 kilometer long transmission line has an impedance of 33 plus j 104 ohm and a total shunt admittance of 10 to the power minus 3 mho. The receiving end load is 50 megawatt at 208 kV with a 0.8 power factor lagging. You have to find out the sending end, find the sending end voltage, current, power factor and power using short line, nominal pi method and exact transmission line, and then compare. Although line is 250 kilometer long, but you consider short line assumption, then medium and then your long line, right. So, we will use the same data, So, Z is given 33 plus j 104 is equal to 109.11 angle 72.4 degree ohm, y is equal to z 10 to the power minus 3 mho. Siemens I am not writing, I prefer to write mho, right. So, writing mho. Receiving end load is 50 megawatt at 208 kV and 0.8 lagging power factor. So, first is you have to find out the your current. So, it is your it is 50 that your receiving end load is 50 megawatt, right. So, your it is your root 3 V I cos phi is equal to 50, but current angle is also taken because power factor is 0.8 lagging. So, we are writing IR is equal to 50 by root 3 208 into 0.8 and angle minus 36.87 degree. So, IR is equal to this one you this is in amp, this is your what you call this 50 is a megawatt and this 208 is a kilovolt. So, that is why this current will be kilo ampere, right. So, IR is equal to 0.173 angle minus 36.87 degree kilo ampere. So, phase voltage 200 upon root 3. So, 120.08 angle 0 degree kV. Now, first you consider this is a short line approximation. Short line means Vs is equal to Vr plus Iz. So, substitute Vr then I and then Z, right. You will get Vs is equal to 135.87 angle 4.62 degree kilovolt, right. And therefore, sending end voltage line to line multiply this one by root 3, you will get 235.33 angle 4.62 degree kV, right. And for a short line sending end current is equal to receiving end current is equal to this one 0.173 angle minus 36.87 degree kilo ampere for the short line, right. Therefore, your sending end sending end power factor I have told you that your current is minus 36.8 and voltage is your what you call angle is 4.6. So, once again I am making it, suppose this is your reference line, this is your reference line and your voltage is your 235.33 sending end voltage 4.62 degree. So, from this reference line this is your Vs and this angle is your 4.62 degree, right. And current is your what you call minus 36.87. So, this is your current, right, IR this thing your what you call and IR is equal to IS, this is Vs IS for short line IR is equal to IS. So, this angle is equal to 36.87 degree, this sending end voltage sending end current, but let me tell you this IR is equal to actually IS sending end voltage for short line, right. So, power factor angle will be angle between this voltage and current. So, it will be 4.62 plus 36.87, this is what I have done here, right. So, that means that power factor angle this thing will be actually directly I am writing that power factor angle is 36.87 degree plus 4.62. So, basically it is cosine of this thing. So, 0.75 and sending end power is equal to root 3 sending end voltage this line to line into that current this thing your 173 into the power factor this 0.75, right. So, this is 52.88 megawatt, this is for short line, right. After that we will put in a tabular form and you will see the difference. When the same with the same data when you consider the nominal pi method, it is A is equal to D 1 plus y z by 2, you compute you will get 0.9481 angle just 1 degree, right. And B is equal to Z. So, 109.11 angle 72.4 degree and C is equal to y into 1 plus y z by 4, that will become approximately j into 10 to the power minus 3. And we know Vs is equal to AVR plus BIR, you substitute here all the parameter A, VR, B and IR, you substitute all, you will get sending end voltage 129.817 angle 5.72 degree kV. Therefore, Vs line to line will be root 3 into this 129.817, that is your 224.85 angle 5.72 degree kV, right. This is line to line voltage. And next is that I sending end current Is is equal to CVR plus DIR, that is your put CD value VR IR value here, right. All you put you will get Is is equal to 0.135 angle 10.23 degree kilo ampere. Therefore, this is this one you take this reference line and Vs line to line is given 5.72 degree. So, this is Vs 5.72 degree and current angle Is is angle 10.23 degree. So, this is your Is from the reference line 10.23 degree. So, you have to get the angle between voltage and current Vs and Is. So, it will become your 10.23 minus 5.72, right. That means this one, that means your this one, this angle you have to find out, this angle, right, and this angle actually comes 4.51 degree, right. So, that means the sending end power factor is cosine 4.51 degree, right, that is 0.997, and it is leading power factor because current Is actually leading the voltage, right. Previous case you have seen that it is lagging, current is lagging, right, from Vs it is lagging, right, but that is for short line, and for this one you have seen that current sending end actually leading the your voltage, right, that is why it is a leading power factor 0.997. So, and here I have written Is is leading Vs and by 10.23 minus 5.72 degree, that is 4.51 degree. So, Ps is equal to root 3 224.85, and this is the current in kilo ampere into the power factor 0.997. So, Ps is equal to 52.4 megawatt, that is the sending end power, right. Then last one is that exact transmission line equation, that is your tan hyperbolic, right, those things whatever you have got cosine, sine, tan, everything. So, first you find out the gamma L is equal to root over z y L. We have seen that gamma L actually just in the previous example you have seen that gamma L root over z y, capital Z capital Y. You substitute all capital Z capital Y values because all are known to you, you will get 0.33 angle 81.2 degree, right. So, ZC is equal to root over ZY. So, small zy is equal to root over capital ZY. This was also you have seen, you put Z and Y values, you will get 330.31 angle minus 8.8 degree. Now, A is equal to D is equal to cos hyperbolic gamma L, put all this value, you will get it 0.9481 angle 1 degree, right. Sin hyperbolic gamma L is equal to, you will get 0.33 angle 81.2 degree, right, and B is equal to ZC sin hyperbolic gamma L, that will get 109 angle 72.4, and C is equal to sin hyperbolic gamma L upon ZC. You substitute all the values, you will almost get the same value J into your J into 10 to the power minus 3. Now, sending end voltage Vs is equal to AVR plus BIR. So, A, VR, B and IR you substitute here, all these values have been substituted, right, and you will get it Vs is equal to 129.806 angle 5.72 degree kilovolt, right. Therefore, sending end voltage line to line multiply by root 3 into this one 224.83 angle 5.72 degree kilovolt. Now, similarly, sending end current Is is equal to CVR plus DIR, C is known, D is known, VR, IR all known, you substitute here, you substitute this thing, not repeating again, but you substitute all these values, only thing is this is in kV. So, this is in kilo ampere. So, this drop will be this part will be in terms of kilovolt, right. So, in this case if you compute, right, using your calculator, you will get that your what you call this Is is equal to 0.135 angle 10.23 degree kilo ampere, right, and in this case also that Vs angle is 5.72 degree, right, and current is 10.23 degree from a reference line if you take the same as before. So, current actually is leading the sending end voltage here also. So, power factor will be cosine 10.23 minus 5.72 degree, same as before, that is 0.997 leading. So, sending end power is equal to root 3 into VR into this current magnitude into 0.997 power factor, that is 52.4 megawatt, right. So, if you compare these three cases, short line, nominal pi method and exact method, for the short line case that your sending a line to line voltage is 235.33 kV, but for nominal pi method sending end voltage is 224.85 kV and for exact method also 224.83. So, nominal pi and exact both are more or less same, but for short line your this is actually 235.33 kV, right, for the short line. Now, for sending and magnitude of current, this is 0.173 kilo ampere, but here it is 0.135 kilo ampere, here it is 0.135 kilo ampere. These two are almost same, these two are same, but here it is slightly more. So, what happens actually when you are considering the shunt capacitor, right, sorry, the charging capacitor, right. So, basically it injects your what you call in the line that your reactive current, right. So, in that case what happened that to some extent that current has two component, right, your this thing, that is one is real component, another is your reactive component. So, when you are in that charging capacitance actually injecting reactive current, so the reactive component of the current will be slightly less, right. So, and in that case when you take the magnitude of the current, so that is why this current will be less than this one, because here no charging admittance is considered for short line, but for this one or this one those things have been considered, that is why current is slightly less than this one, this is inevitable, right. And power factor, when you are not considering anything, right, for a short line no charging and it is 0.75, but if you consider nominal pi or exact method, the power factor is much improved 0.997 and both are same. This is again the same philosophy, this is happening due to consideration of charging admittance. So, for long line, right, you cannot ignore the charging admittance, and for the short line case that your sending end power 52.88 megawatt, but in the case of nominal pi your exact method it is slightly less 52.4, here also 52.4, because of that reactive current injection I told you the current magnitude is less. So, this current is slightly less, right, and this is a little higher. So, if you think this way, that means line loss will be for the nominal pi or exact will be slightly less compared to the short line your what you call consideration, right. So, this is example I gave short line, nominal pi and exact method, but one thing you can see nominal pi is almost as accurate as exact method. So, that is why you will find for all transmission line load flow studies charging admittance they are considering basically nominal pi method, right, if line is too long. So, this is for overhead transmission line. Next is, so for this transmission line some 6 different examples I have given to you, right, and this will clear your ideas that different type of problem, right. Now, next is that your voltage waves, right. So, by using equation 26 and 27, right. So, I will show you 26 and 27 just few seconds, right. This if you recall, this is your equation 26. This is your equation 26, V x is equal to C 1 e to the power gamma x plus C 2 e to the power minus gamma x, right. This is equation 26, and gamma, that your propagation constant we have taken alpha plus z beta, right. So, using 26 and 27 means you put this gamma value here, you put the gamma value here. If you do so, then it will the 26 and 27 it will become V x is equal to your C 1 e to the power alpha x plus your into e to the power j beta x, because it is e to the power actually alpha plus j beta x. So, we are separating it like e to the power alpha x into e to the power j beta x plus C 2 e to the power minus alpha x into e to the power minus j beta x, right. This is equation 49. Now, this equation 49 you have to transform to time domain, because this value actually it is a RMS value, this V x value actually it is a RMS value. So, if you transform it to a time domain, right, the instantaneous voltage is a function of time t and x, you can give it, you can write V function it is t x t comma x, that is V is a function of time and the distance x, right, is equal to, as this is RMS value, it will be root 2 into real part of this one C 1 e to the power alpha x, then e to the power j omega t plus beta x, because we are considering in time domain, that is why we are writing e to the power j omega t plus beta x, right, and this is RMS value. So, same as before, whatever you have studied for your AC circuit theory, right, philosophy same, right, plus root 2 real part of C2 e to the power minus x into e to the power j omega t minus beta x, right. So, this is that your time this equation we are transforming into your time domain, right. So, and this is equation 50. But after that whatever I said, I wrote here that note that V x in equation 49 is the RMS phasor value of voltage at any point along the line. That means, this one we are transforming into time domain, right, and x is the distance that is measured from the receiving end. So, x increases, that is moving from the receiving end to sending end, the first term becomes larger, right. So, if the length is increasing, because when you are deriving the expression for long line, have considered that from the your distance is considered from receiving end to sending end. I mean, when you are moving from receiving end to sending end, x is increasing. So, when x increases e to the power alpha x, right. So, this term will increase, right. So, that is why the first term becomes larger because of e to the power alpha x, and is called the incident wave, right. And the second term e to the power minus alpha x becomes smaller as x is increasing, because it is e to the power minus alpha x, and this is called the reflected wave. So, one is incident wave, another is called the reflected wave, right. So, at any point along that line, voltage is the sum of two components. That means, this term we are defining as V 1 T x, the first term, and the second term we are defining as V 2 T x, right. So, that means V 1 T x, that is V 1 is a function of T x root 2 C 1 e to the power alpha x, and if you take this cosine real of that your real part of this one, it will be cosine omega t plus beta x. So, this part is cosine omega t plus beta x, this is 52, and the second term V 2 T x will be root 2 C 2 e to the power minus alpha x, it will be cosine omega t minus beta x, because here e to the power j omega t minus beta x, if you do the real part. So, it will be C 2 e to the power minus alpha x cosine of omega t minus beta x, right. This is equation 53. So, this is the expression for V 1 and this is the expression for V 2, right, T x. Now, as we move along the line, so if you move along the line, then what will happen, that your that equation 52 and 53, it's behave like a travelling wave, right, because one is incident wave, another is reflected one. Now, you consider the reflected wave, we will consider this reflected wave part, this part, right, reflected wave. So, that is V 2 T x, and imagine that we are riding along with the wave, and imagine that we are riding along with the waves. That means, if you want to see the peak amplitude of the travelling wave, the way that wave speed, what will be the wave speed, and if you also move along with the same speed, then only you can observe the peak. So, imagine that your what you call we are riding along with the wave, right. We are considering the reflected wave. For observing instantaneous value, peak amplitude requires that omega t minus beta x is equal to 2 k pi. That means, this one, that means your this one that you want that cos, if you want to, this is the peak value, if you want root 2 c to the power minus alpha x, whatever be the peak value, that cosine omega 2 minus beta x is equal to 1, right. That means, your cosine your omega t minus beta x equal to 1, right, is equal to, you can write cosine 2 k pi k, or 2 I can write is equal to 2 k pi, I put like this, right, your cosine of 2 k pi, right. So, that means, omega 2 minus beta x is equal to 2 k pi, it is a general thing, right. If k is equal to 0, cos 0 1, if k is equal to 1, cos 2 pi also 360 degree 1, and so on. So, omega t minus beta x will be 2 k pi. So, that means, for observing the instantaneous your what you call that value, peak amplitude requires that omega t minus beta x this should be 1, that means, omega t minus beta x must be equal to 2 k pi, just I told you, right. That means, my x is equal to omega by beta t minus 2 k pi upon beta, this is equation 4, right. Now, to keep up with the wave and observe the peak amplitude, we must travel with the wave speed, right. That means, whatever is the speed, right, if you want to observe that peak, then you have to travel with that. So, in that case what will happen, that you take the derivative with respect to time, that d for equation 54. So, dx upon dt you find out, right, from the dx upon dt means basically it will be omega by beta, right. Therefore, dx by dt will be omega upon beta, right. This is equation 55. Thus, the velocity of propagation is given by v is equal to omega by beta, that is dx upon dt, omega is equal to 2 pi f divided by beta. This is equation 56, right. So, this is the velocity of propagation. Now, a complete voltage cycle along the line I have written here correspond to a change of 2 pi radian in the angular argument beta x, right. The corresponding line length x is equal to lambda, right, is defined as the wavelength. If beta you express in radian per meter, beta is expressed in radian per meter. That meaning is that a complete voltage cycle along the along the line correspond to a change of 2 pi radian in the angular argument beta x, right. So, in that case the corresponding line length x is equal to lambda is defined as the wavelength. That means, that if beta x is equal to 2 pi, that is x is equal to actually lambda, right. So, that is why here we are putting that when x is equal to lambda, beta lambda is equal to 2 pi. So, wavelength lambda is equal to 2 pi by beta. Only one thing I will tell you, generally actually lambda, this has become my habit, I write like this, but actually it is like this, right. Actually it is like this, but so you forgive me. So, this has become my habit. So, I write like this, right. So, beta lambda is equal to 2 pi. So, lambda is equal to your 2 pi by beta, right. So, this is actually your what you call that wavelength, right. Now, some more important thing. So, while line losses are neglected, that means G should be 0 and R should be 0, right. So, in that case if line losses are neglected, then the real part of the propagation constant alpha will become 0, right. That means, from equation 27 gamma is equal to alpha plus j beta, that is equal to root over small z small y. So, small j all nomenclature was given in the beginning of this topic. So, r plus j omega l into g plus j omega c, right. So, as r is 0, g is 0, you substitute r 0 g 0 here, you will get square root j square omega square L c, that will get j omega root over L c. So, no real part, that means alpha is equal to 0 and beta is equal to omega root over L c. This is happening when line is a lossless, we are assuming a lossless line. Therefore, equation 29, the characteristic impedance we know, the Z c is equal to root over small z upon small y, and small z is equal to root over r plus j omega l divided by g plus j omega c, but r is 0, g is 0. So, if you put r is 0, g is 0, j omega will be cancelled, and ultimately it will become Z c will simply become root over L by c, right. So, Z c actually is a pure resistive, it is purely resistive, right. There is no complex part here, root over L by c is a purely your resistive. Then that means which is commonly referred to as the surge impedance, right. So, Z c actually common to referred to as the surge impedance. Its value varies between 250 ohm and 400 ohm in the case of overhead transmission line, and between 40 and 60 ohm in case of underground cables, right. Thank you, then I will come back.